Hello, everyone. Nice to see you again. I know it's a tough spot, so I'm going to give you a very nice and chill talk about a simple topic, compilation. And you can like chill in the background and like rest a bit. So I wanted to talk about compilation because I love the topic, and I realized that I've got way too much content, so I'm going to have to be a bit fast. Sorry. But I wanted to take the perspective of what does a compiler do? How does it apply explicitly to the context of Rust-C? And what can we learn to make the compilation faster for Rust? And I've also done some experiments on my own project. Some of them work, some of them didn't work. So hopefully we're going to learn a things or two. So who am I? I'm Benjamin Bouvier, as you heard. I worked at Mozilla previously on the SpiderMonkey VM, which is the JavaScript and WebAssembly virtual machine for Firefox, the web browser. And then after that, I worked at Embark Studios, which is a video game company on a video game engine that is based on WebAssembly plugins entirely, with like hot reloading and stuff like that. And now I work at Element on the Matrix protocol, which is a protocol for messaging that is entirely decentralized and end-to-end encrypted. And so lots of Rust and WebAssembly all over the years. I've also worked on CranLift when I was at Mozilla, which is an alternate compiler, and we'll get back to that later. So I started as an intern at Mozilla, and like the people there were like, "What would you like to work on?" And as I was very naive, I was just out of school. I said, "Give me something hard." And they were like, "Cool, we'll put you in the compiler team then." Compilers are quite hard. One day I woke up, I received an email that told me you were the author of a commit that we bisected to be the cause of this bug. This is Google Maps, and as you can see, the borders between the countries are kind of broken. I implemented some optimization paths in JavaScript. The good news was it would be used by Google Maps eventually. The bad news was it was not working. It was a bit triggering too aggressively. So I learned the power of assertions and invariants over the last days of debugging this. And this one is actually nice. Like when you're working on compilers, usually you will have generated code that will crash at some point. So you don't have access to any source code, right? Because you generated the code yourself. You don't necessarily have all the dwarf annotations to map it to the original source code. So all you can do is take your eyes, cry a bit, and then start to debug, trying to figure out what was generated and take it back from there. So yeah, compilers are hard, I can confirm that. But there are some steps that are quite easy to figure out at a very high level perspective. One, spoiler alert, I'm not a specialist on the Rust-C compiler. There are some Rust-C compiler specialists here, and if you have questions that are very specific to Rust-C, go ask them. I've like gone through many blog posts and articles and podcasts to try to gather information about how Rust-C works, and I'm trying to distill that into this presentation. All right. So that's the plan. What are we talking about when we talk about compile times? Is it slow to compile? What does a compiler do? And what can we do to make it faster? And then there is an appendix, but I doubt that we'll have time to look at it. All right, so compile times. There are two sorts of compile times. The cold build times, the first time you build your project, it will take some time and it will put things into a cache. And then you do some changes in your code. And in that case, it will partially rebuild your code, right? That's what the incremental compilation is all about. And both of them matter, actually. Since Rust is a source-based language, you do, like the cold build times will matter to end users. And if you're building a library, the end users will be other library developers. But if you're making a binary, well, the end users are the people installing your binary by hand with cargo install. But that doesn't really matter to end users who are like just installing a release that you built ahead of time. And the partial rebuild times are more important for developers in general. You want to have the perception of speed and have a really short hacks compile test cycle. So fortunately for that, there is the language server protocol that was mentioned earlier in another talk. If you're not using it, lucky you, you're going to have like 10x speedups in your workflow. So that's really great. Otherwise, I would really imagine that everybody's using that on a day-to-day basis. All right, so let's take some perspective back from like the problem of compilation and compile times. That's my interpretation of what Rust means to me. Programmers are imperfect, and that's perfectly fine. We will make mistakes. We will have errors. We will not think about some situations that are problematic in our code. So we rely on the compiler, holding our hands and trying to find all the errors at compile time so that we don't have them at runtime. And that's very nice, and I love that. And at the same time, we want the code to be super fast and to run super fast. So there's a theoretical trade-off here. You do more work at the compile time to make sure that you don't run, like you have all these static analysis and you don't run into this category of errors so that you don't have them at runtime and you still have very fast code at runtime. Some other languages don't care about these kind of paradigms and say that programmers are like must be good and must learn to not make mistakes, and they get the best speed out of that. So different point of view. Not one is better or worse than the other. Well, so why is compiling Rust kind of slow? There are some language features that make it fast and safe, but that requires some engineering work in the compiler on the one hand. And on the other hand, I think there's a lot of historical reasons, like the fact that it's using LLVM, which is a compiler infrastructure that has been there for years and years, decades even, and it's not prioritizing the compile time, but the quality of the generated code. So it will try to make your code run really fast at the cost of having higher compile times. Also, it was written as what we call a batch compiler, where it will take an entire crate and try to compile it, instead of trying to do as minimum work as possible on as little code as possible at a time, which would be an on-demand incremental compiler. If you compare Rusty with Rust Analyzer is more an in-demand computation framework and compiler in general. And of course, there is some accidental slowness that happens with all the software in the world, where you don't optimize for something because you don't realize it's a problem. You take a profiler, profile your program, figure out something that is slow, and then you optimize it. Okay, so a compiler takes your source code, like at the top, and transforms it to assembly code. Your machine doesn't speak English or any human language, unfortunately. It only speaks assembly code, and which is like binary encoded, and it's not practical for human to use it. So we made software that can automate this for us, and that's really what a compiler is. It's translating from one language to another language, one that is human to one that is for a machine. But compilers may be kind of slow. It's like usually understood as a sequence of phases that has its own kinds of inputs and outputs, and there are graph algorithms all over the place. And these graphs, they represent the control flow of your program, or like the sequences of statements in a block of your program. You can have cycles in those graphs, because your programs will have loops. So a block will like circle back to the top of the loop, for instance. And that makes for very fun, slow algorithms that, in the worst case, can be quadratic in terms of the compiler's input size. So they can be super slow. We'll get back to that. Okay, so I'm going to focus on one project that I've been working on for the last 2 years. It's a SDK for the matrix protocol, messaging protocol I was mentioning earlier. It's a library, not a final executable, and that's actually important in terms of the profile of the compile times and all of that. We'll also, I'm doing some benchmarks on my personal machine, another one than this one that has 20 logical cores, etc. It's running on Linux. And the project has around 200,000 lines of Rust code if you don't count the comments. And our baseline for today will be that it takes around 66 seconds to compile a debug build. As I'm a developer, I'm more interested in like the code build times of a dev profile, but you could argue that if you improve the code times, you will improve the incremental times as well, usually, because these are using the same mechanics under the hood, just not on the same scale. Okay, so all the phases of compilation, usually you can represent them like that. There is the parsing, then you will emit some intermediate representation called IR subsequently. On this IR, you can either do some analysis on your program or perform some optimization, or why not both if you want to. And then rinse and repeat. If you want, you can translate this IR to another IR that is more suited for another problem that you want to solve with your compiler. And you get back to that until you're happy with the IR. And then you will generate the machine code from a low-level IR, usually. Okay, so the first step is parsing. On the right, you can see parts of the output of the parser for a simple Hello World program. So the parsing is actually two phases. There is the lexing, where first the source file is decomposed into tokens. Here's the literal, is the FN keyword, is the an arrow, etc., etc. And then the parsing will reconstruct structure from this token stream, where it will say, oh, this is actually a function, and these are the function parameters, and this is the function signature, and all of that. These parse nodes will form the abstract syntax tree, also known as the AST, and it only contains source-related information, nothing that is specific to your architecture or platform or target at this point. From there, we will continue with the intermediate representations. So there's a trade-off there. It takes some time to emit one, so you got to face a very specific problem that you want to solve before deciding we should have a new IR. And so you will have as many IRs as you decide that there are interesting problems that might be IR specific. Just out of curiosity, how many IR do you think there are in the Rust compiler? 2, 3, 4, 5 maybe? No, 4 is actually the right answer. So after you have the AST, your Rust code is translated into the high-level IR that is used for type checking. So you can have really quick type checking. Then there is the typed high-level IR. I don't know if it's pronounced there or dire. Sounds pretty cool to me. It's used for exhaustiveness pattern checking. What does it mean? When you have a match statement, it makes sure that you are actually exhaustively checking all the cases, and safety checking. So something that is unsafe must not be called without an unsafe block, etc. And then you have the famous MIR, the mid-level IR, which is some kind of simplified Rust. And this one is used for our good friend, the borrowed checker, and as well as some optimization phases. And then you have the LLVM IR. So LLVM stands for low-level virtual machine, but it's an acronym that lost completely its meaning, like the VM doesn't really mean anything anymore in this context. And this one is the input for LLVM, the CodeJet backend that will generate the machine code. It will also have many optimization passes, and it will then be converted into the machine code. Okay, this is the mere representation of a simple Hello World program. So you can see it's encoding, so the partial mirror representation, there are many more things actually. And this is before the optimizations. So you can see some interesting things here. The scopes, they represent a basic block of your program, so a block of linear statements that will be executed in linear order. And then at the end of a basic block, you will have an instruction, a hint towards where should we go after we've executed this basic block of instructions. This is the return at the bottom. And so you can see the BB0 returns to the BB1, and the BB1 will go to BB2. So it's just very linear in this case. But if you have loops, you can imagine that BB1 could return back to BB0, for instance. And then you have something that resembles some Rust code. _6 is a variable that holds a static string, and then we create some arguments in _3, and then we pass those arguments to the print function in the _2 definition. So some questions. What generates so much IR? Because our problem is that we have a lot of IR. And if we get, like if you remember the representation of the phases, the more work you have upfront, the more input you have upfront, the bigger the input upfront. Well, usually the bigger the input in the downstream phases as well. So we have to understand why there is so much IR to understand why we have so much generated code and why it takes so long to compile in general. So one source of getting lots of IR is the build scripts and proc macros that we all love. I think they're key to the success of Rust, and we shouldn't get rid of them. But they bring a few drawbacks in that they must always be recompiled, so they're a rock in the shoe when you're using incremental compilation. They will also stall the pipeline compilation with cargo. We'll get back to that later. And it's also quite easy to not see that it's generating a lot of code. I imagine that probably everybody who's coded Rust in this room has used 30 in the past. I would encourage you to look at the output of the macros, the derived macros that 30 is making. It's generating a lot of code, which is very nice because then you can have serialization and deserialization for free for many types and all of that. But it's interesting to just see how much code it generates to do that. So a pragmatic rule of thumb, if you can avoid using a proc macro, avoid using a proc macro. That's really nice. And it's, in my opinion, also makes the code sometimes easier to read and to maintain this. Okay, so another source of generating a lot of IR is inlining. Basically, you have a function that calls another function, and the function that is called, the callee, will be, like its function bodies, will be entirely copied and pasted into the body of the function that is calling it. And that's super nice, but that will create super large functions because you can actually inline several levels of function calls. And it's also kind of fragile in the sense that it's based on a lot of heuristics, like depends on how many statements you have in your function, the size of your function, the one that is called, the one that is the caller, etc., how many loop levels you have in your functions, and stuff like that. Usually, Rust is very eager to try to inline all the things within a single crate. And you can actually add an annotation inline on top of a function, and it's a hint to say this may be inlined across crates. I didn't say this will be inlined, because this acts as a hint to the compiler that based on the heuristics of the compiler, it may be inlined. But if you don't have this annotation, the functions that you are exporting from a crate may not get inlined at all. Let's look at an example. So I think it's nice because it shows something that is kind of obvious when you inline the indirect funcall function into its caller, but also something that is a bit less obvious. So the indirect funcall function takes a Boolean to decide whether it's like entering the first branch or the second branch, and then it also takes what we sometimes call a fat pointer, so a pointer to a trait that will use a vtable for the function call, so an indirect call, right? Now, when we inline indirect funcall into main, it looks like this. And this looks kind of dumb, right? I mean, it's obvious that we can get rid of the else branch in that case, but there is something more, actually. In that case, we can also see that the din to string implementation is, well, the pointer actually refers to the I32 type. So we can devirtualize the function call and not use an indirect function call in that case. And that becomes stat after optimization. And if you're an astute compiler hacker, you would even say, well, the result is not used, so probably like the function main would be empty. And you would be totally right. What can we do about inlining? Not much. As I said, it's a bit random and fragile. You can add inline never to say, I don't want this function to be ever inlined. And that can be actually a trick for generics. If you have a generic function that takes a parameter that's, for instance, taking of a type impl as ref, and then you have a large function body, you will usually like have something to call as ref at the beginning and then the large function body. You can take the large function body, put it in a function that is never inlined, call the asref on the other part, and then pass the result of asref to the never inline function, and you make sure that your generic function, every time it's instantiated, will not duplicate the large function body every single time. Can also tweak the inline heuristics, but I wouldn't play this game for determinism. Like the only two cases where it might make sense is if you want absolutely to disable inlining all the time, so you put the value to 0, or if you want to inline all the things all the time, and you put a very large value. And yeah, I hinted at generics. So these type parameters are super nice Rust language feature. And every time you will use one of these generic functions, it will wait until you know the type for sure statically and create a copy of the entire IR. It's as if you were copying and pasting the entire functions body for each type that is instantiated. It gets really nice because like it makes your code run super fast. You will have optimizations that are run on each monomorphized version of your generic function. So optimizations that can be specific to each monomorphization in particular. But it brings some costs as well. You will have duplicated parts of your functions body. The generics can be inlined as well. And also across, well, within a single crate, the generics can be duplicated even for the same type in case you're splitting the IR that you're sending to LLVM for compilation in parallel. But across different crates, every time you will actually export a public generic function, this function will be duplicated every time it's instantiated in one of the dependent crates. So that may create a lot of duplication. But there's been an idea floating in the air. What if we didn't copy the generics once per crate? So think of your dependencies as a tree where the leaves are the final binaries, and on the top of your tree you have the dependencies themselves. So if you have a dependency crate that instantiated a generic function, every crate that depended on it could reuse that instantiation. That's pretty nice. And it's been a nightly option for a few months, at least. And I've used it on my project. And it was actually surprising to see that it was almost a slowdown in terms of compile times. So why is that? Why does that happen? There's a tool that is called Cargo LLVM lines, and it will show you the copy of the number of copies of your functions that are generic with the size in terms of LLVM lines. So we can suppose this is equivalent to LLVM IR and tell you which are the functions that are generic in your code and how many times they're actually instantiated. This is the top 15 functions that are duplicated in my project, and none of them are actually under my control, kind of, in the sense that there is not a single function that I've defined myself. So there's not much I can do about that. And I suppose that if you add up all the numbers, would be maybe 10 to 15% of the code is being duplicated, but the shared generics feature is not actually done yet. That's why it's only nightly at the moment. So I expect that this might get better in the future. All right, all of these parts up to now, we call it the front end, because then later we will package this IR, so the mir, which is the last IR that we deal with, into the LLVM IR and send that to the backend for compilation. Up to recently, it was all done sequentially per crate, but of course, this is something where the Rust compiler itself can use parallelism. Like if you have two functions or two modules and they don't have to interact with each other, you could compile the functions or the modules in parallel maybe easily well. So there's a nightly option, Z-threads, that you can configure to the number of threads that you want to use in parallel for executing the front-end bits of the compiler. It's always recommended to use 8 threads. And I was like, come on, my machine has like 20 cores. Why would I use 8 threads? I'm going to use more. But then you run into thread contention, I suppose, like data structures that are protected against locks and mutexes and in the Rust C compiler itself. And that actually gives you some overhead that is not neglectable. So you do want to use actually 8 threads. That's how you get the best speed up in terms of compile times. And from 60 seconds to 45 is something around 30% speed up. So it's quite amazing. I've been told by Liquid from the compiler team that this might get stabilized soon enough. So we'll just get compile time, better compile times for free. And something else that I tried was running the test suite, because all these like nightly options, they are fancy, like if they can improve my compile time. But if I can decide how to compile, I will compile my code wrong, right? Because that can be very fast, but then like at execution, this will be useless, right? So this is actually compiling correct code much faster. So this is like perfect, exactly what we expect from the compiler, in fact. And then you have optimizations, passes, that will reduce or increase the amount of IR that is generated by the compiler. I've made some list of like optimizations that are quite common in compilers. For instance, constant propagation. If your code contains 1 plus 2, well, I can infer that it's actually 3, right? There are some optimizations that are less obvious, like in peephole optimizations, you will see that if you have a value that is an integer, you multiply it by 2, it's actually better to do an addition of the value with itself, because your CPU prefers doing addition to a multiplication. Loop invariant conversion is when you have something, a value that is computed to be constant in your loop. Instead of computing it once per loop iteration, you will hoist it above the loop. You don't have to do it yourself. The compiler can realize that. Of course, this is also something you could do yourself if you wanted to. And there is the kind of opposite optimization, loop unrolling, where it will like see, like take an iteration of your loop and manually paste it with like the value of the index multiple times. It will do that sometimes for realizing later on that you can use SIMD instructions to make your code faster. Well, there are many optimizations. The tweet on the right was something that I found nice because it actually shows one of the easy optimizations that we ran into earlier in the example about inlining. If you have if true, you can just remove it, because if true is always happening. All right, the last step is code generation. We will use the LLVM backend, like used for tons of programming languages, not only Rust. I think it was meant for C at the beginning with the Clang compiler. It's the industry leader in compilation with GCC. And usually Rust-C will group the LLVM IR into what it calls code gen units and send them to LLVM IR so that LLVM, so that LLVM can compile it in parallel. So that's one of the few places where you have parallelism. We had the parallel front end, we have the parallel backend now. But you can actually use other compiler backends if you want to. There is CGGCC that was mentioned. You can use GCC as the compiler backend. So all the front end goes through Rust, and then it's converted into some GCC IR, I suppose, and it will be compiled into machine code at the end. If you're even more adventurous, you can use GCCRS, which is an entire front end and back end alternative for compiling Rust. But there's also this other compiler project I've worked on, CraneLift, written in pure Rust, can emit machine code for ARM64 and x86 64 bits and other platforms. It was designed in the first place to compile WebAssembly binaries, because the intent was to use it in Firefox for compilation of WebAssembly. And WebAssembly, for the sake of this talk, you can consider it's a pre-optimized IR. The use case was just-in-time compilation. So you're going to a website that is making use of WebAssembly. You want the WebAssembly module to be compiled real fast. because you're like, as a visitor of the website, you're not going to wait 10 minutes for the WASM binary to be compiled into machine code, right? And WebAssembly has been designed with functions as the compilation unit in mind. It has like a nice index at the beginning of this is where all the functions are, the function bodies are in the module. And so it makes it super easy to compile functions in parallel, in particular. So I made another experiment, try to compile my project with CraneLift and see what the results are. So I gained 4 seconds overall, and it still passes all tests. That's when I'm compiling only my workspace crates with CraneLift. If I'm trying to compile everything, the workspace and the dependencies, it compiles even faster, but this time the tests are not passing because it's tripping up on some SIMD instructions that are not yet implemented in the CG CraneLift backend. So there's that, but it's actually kind of nice. And I was like, well, 4 seconds, it's kind of disappointing. I was like expecting more. It's supposed to be super fast. It's written in Rust after all. It's supposed to be lightweight. What's going on? So there's a tool that you can use to see where Rust C is spending time in all the phases that I talked about. It's the self-profiling framework. So there are some lines that I gathered from a blog post from famous Faster Than Lime, like magical invocations that allows you to compile a single crate with the self-profiling harness, and then it will give you a Chrome profile. No, sorry, it will give you first a profile that you can convert to a Chrome-compatible profile, and then you can use any Chrome profile reader to take a look at what's going on. And on my project, well, you can see like all the steps, analysis. You can even see mentions of mir here and there, generating crate metadata. CodeGen crate is the green part around the 10 seconds boundary, but you can see it's not spending so much time generating code. And that makes sense. I told you my project is a library. So we're not like generating lots of code in a library. That's kind of expected because our users will be generating lots of code at the end. So it's maybe 1 second out of 13. That's for a single crate. That is one of the toy examples in this SDK. And so if it's only 1 second over 13, I can't expect a big speed up. Even if it was like super fast to do the code generation, that would only shave off 1 second out of the entire profile, right? So the rest of the time spent in the analysis and generation of crate metadata is what takes time in that case. So small detour about the Amdahl's law. If you optimize something that takes n% of your total execution time, the best you can spare in terms of time is n% of the total. So you will have maximum speedup that is conditioned on that value, right? If you can optimize 50% of your execution time, then you can have at most twice 2x speedup, because you still have to execute the first part that is not optimized. And there's like a fun game we can play about that. Imagine that you're going on a hike for 9 kilometers. You've already crossed 3 of them, took you 1 hour. So your average speed was 3 kilometers per hour on that part of the hike. What is the maximum theoretical average speed you can achieve overall? And this is the same thing that I just talked about. If you had the ability to teleport instantaneously to the end of the hike, well, you would have gone over 9 kilometers, and it would still have taken you 1 hour for the 3 initial kilometers. So your maximum speed is 9 kilometers per hour. And you've achieved times 3 speedup in that case. But I noticed something weird during self-profiling. There is, like, when I clicked around on the profile, I saw that during analysis, there are some type-checking function that takes a lot of time. And on the bottom right, you can see that there is a function name, and that's a function name that is in my project. So I tried to look at it to see what it was doing, because it didn't seem to be a big deal, but it seemed to take a long time to type check. So this is the code that does it. Basically, it's using it's a method in a trait using async trait. This is a derived macro that makes it possible to have async in traits before we had the ability to do it kind of natively. So we were using that in a few places, and actually in the other type check block, there was another one that was another function in this trait. So I figured that something might be going wrong. And we're actually hitting what we call a pathological case in RustC. RustC does its best, but it might not be optimized for all kinds of inputs. And on some kind of inputs, it will trip up and actually spend a lot of time computing the result we expect. So my first intuition was that, well, now in stable RC, you can use some functionality for async in traits. Why shouldn't I use that instead of the async trait? Can I do that? And I've rewritten this trait as this thing, now using box futures instead of async directly. So because an async function is kind of equivalent to a function that will return the future. So we can do that. It's a boxed future because it makes it easier in terms of type checking. And also the extra memory allocation is nothing in the grand scheme of things because these functions actually call like the network under the hood. So calling the network will take much more time than the memory allocation. And as soon as I've done that, well, the green squares in the Rust-C self-profile disappears entirely. And if you recall correctly, that was like 1.7 seconds just for type checking one of these functions and the other next to it as well. And that was 7 seconds time reduction just for this crate overall. So I would advise to sometimes look at this for crate that seem to take a long time to type check. You would notice also when you're using the Rust analyzer in particular, you're making a change and it seems like it's taking 6 or 7 seconds to actually show you diagnostics and error messages. If that's the case, it might be hitting some kind of pathological case like that. Well, I say no more type check block. There's a one that is still remaining, but that's for another trait, another function, etc. Okay, so a compiler actually does much more than that. It will do what I explained for each dependency and crate, and then it will try to link all the things into the final binary object. There is some parallelism that is happening here, and is the pipelining of cargo. Every time you compile a crate, first you will generate the metadata for the crate, that is all the public exported functions information, so that the upstream dependencies can actually make use of that dependency. And then, as soon as this metadata has been emitted, you can start compiling generating the code for the current crate and kicking off the compilation process for the crates that depended on this one. And you can see it here. It's like the blue blocks are representing the metadata generation, and the lavender blocks are representing the code generation. So once again, there is not much code generation in my project here. This is the end of the profile, like up to one of the toy programs, but it actually goes way up, more up in the graph, like there are 492 other lines. And at the beginning, it can compile lots and lots of dependencies in parallel. So you see that your CPU is hitting at the beginning of compilation with cargo. But at the end, you may have some more of a profile like that, where it's just compiling one crate at a time. So one trick here would be to splitting your code into multiple crates. And over time, people have often given that advice to do that, because that will give more opportunity to cargo for doing this pipeline trick. But in practice, it may be impractical because you have like not very clean interfaces. All your APIs are very entangled with each other. There is the orphan rule that makes it so that if you have a trait and an implementation, either the trait must be in your crate or the implementation, well, the type you're implementing it for must be in your crate. Otherwise, that would allow any crate to implement random traits for everyone. And it will also add more work to the linker, and the linking part is notoriously slow. So One advice that I would give is that if you don't compile code, it will compile faster. So look at your dependencies in general. Some of them might not be critical. Some of them might be using cargo features that you can disable. Some of them might have lighter alternatives. Some of them might be duplicated, and you can notice that with the cargo deny tool. Like in our project, we have 29 such duplicate dependencies. That can happen when you have two dependencies that make use of the same dependency, but in versions that are not compatible in terms of semantic versioning. So in this case, it will recompile them. And that can happen a lot. If you want to render service to the whole Rust community, you can actually look at these dependencies and update the dependencies so that everybody benefits from not having duplicated dependencies. It's kind of nice. Sometimes it's trivial. Sometimes it's migrating from scene 1 to scene 2, and you just don't understand anything if you haven't touched proc macros in your life like I have. And the other one is you can also have unused dependencies, and it's not uncommon that during the development workflow, you will add a dependency, do some work, and 6 months later, realize you don't need the dependency anymore, and you get rid of it. So you can use cargo udeps, which will compile the code and look at the unused artifacts after it's compiled. So you would need to do that for every platform, architecture, OS, etc. And I made a silly tool that will just basically re-grep the use statements. So it's just looking at the source code text itself and doing search on it. Doesn't need compilation, so it's much faster to run. And it's a bit imprecise, like a machete, but it's really efficient and fast. We don't have much time for this, but basically your linker takes all the compiled objects, connect them into the final binary or library. There are also a thing called link time optimizations, where the linker will try to optimize across all the functions in all the entire program, whereas usually a compiler will focus on a single function at a time or single crate at a time. This will do optimize across all the crates. You have several profiles. The more you go to the bottom, the slower it will be, basically. And this is one of these configuration options that is kind of weird in the cargo toml definition. Like if you put false to LTO, it's different from putting off, like of disabling the LTO. It's not the same thing, right? Makes sense, right? Probably I should write a RFC for this now that I know how to do it, instead of complaining like a stupid person. All right, so linkers, you can try alternate linkers. If you're using, I think by default, we're still using the LD linker. On most platforms, I heard that it will default to LLD soon, which is slightly faster. So you can see like 3 seconds are shaved off the total compile times for my toy example. And there's also another one called Mold on Unix. It makes use of parallelism heavily. So it's kind of in the same ballpark as LLD, which is kind of surprising. But there's now a new contender called Wild, and it's even faster than that. And it's already working on my project, at least. And it has like some exciting features planned for future development, like incremental linking, making your binary and making it possible to link things by patching your binary in a kind of dirty way, which is okay for development purposes. Don't do it in production ever. An alternative would be to use dynamic libraries. I will not go too much into detail. Faster Than Lime has made lots of blog posts and podcasts about this. This is kind of very cutting edge technology, far ahead looking in the future. If you're only compiling a single project now, you could already compile dynamic libraries because Rust supports it, but don't ever share that to anybody else. Keep it on your machine. Otherwise, you're going to run into terrible issues. All right, there is also some work that is done by the compiler team to make the compiler faster. Very interesting project. There is one issue that I would recommend that you take a look at if you're interested in the future developments. And I would like to thank everybody who's making the compiler faster, because there are some people in this room. And just thank you, everyone, for listening.